Okay, so now that we went to the inner magnetosphere, let's go back to the outer again, and more specifically to the actual bow shock of the Earth. Christos already told you some things about jets, but I will focus more on the actual generation mechanism of those localized structure. So let's give a bit an introduction again. So those jets are basically transient localized enhancement of dynamic pressure, which means that as a bulk flow for ions, we have a density and or a velocity enhancement. They appear downstream of the bow shock. Here you see the same sketch Christos showed a few minutes ago. But the idea is that we can see the upstream region. We can see the bow shock, and usually those high velocity jets appear just downstream of it. They have been connected to many phenomena, for example, to magnetopause reconnection and direct plasma penetration. So there is a lot of focus in that area at the moment due to their connection to all those kind of magnetospheric events. So when we talk about jets and shock in general, a very useful classification is between the quasi-parallel and the quasi-perpendicular regions. So when we say quasi-parallel, what we mean is that the angle between the IMF and the normal shock vector is less than 45 degrees. This creates an ion foreshock region, which is the result of the counter-streaming particles that get reflected from the shock, and we get a much more turbulent environment there. So usually we separate the shock into those two regions, and also the corresponding magnetosheath and the jets that we find here. So my initial plan for this talk was to give you a detailed overview of the statistics between the jets that are found in the different environments. But there has been some recent results that I had that I wanted to share with you that are to be submitted hopefully in the next couple of days, that have to do with a way to actually generate jets as a direct consequence of the dynamical shock evolution of the Earth. So let's start a bit with how we believe so far that those jets are created and appear in the downstream environment. So one of the most prominent mechanisms of how the jets are created is the so-called shock ripple mechanism. In this case, basically we have the solar wind getting deaccelerated as it crosses the bow shock. And by following the Rankine-Hugoniot relations, one can find that the bulk properties will experience this kind of heating and compression that we usually observe when we cross a shock transition. But there are those ripples in the bow shock. And if a part of the flow of the solar wind passes through them, we can follow the actual theoretical approach and see that this part will have a less deaccelerated flow. As a result, it will appear as a relative enhancement compared to the background because the rest of the solar wind has been heavily thermalized through the crossing. Now, there have been also other kind of models that explain how jets are created. Some of them rely on the existence of rotational discontinuities in the solar wind and the interaction with the bow shock. More recently, there have been some studies that connect the jets to foreshock structures. Those are the results in the interaction of the counter-streaming particles with the incoming solar wind, and they appear usually in the ion foreshock region, which, just to remind you, is like the upstream region of the quasi-parallel shock. Now, as I told you, there was another term that in the previous slide, which is the shock reformation idea. This idea has been going on for quite many years, and basically it's a model of the quasi-parallel shock, mostly on how, like in smaller scales, what is really happening in a shock crossing. So you see here on the left a simulation result from a peak simulation back from 2002. As you see in the y-axis, we see how time evolves, and in the x-axis, we have a projection of space. Basically, what we see here is that an initial ramp of a shock going from like a low IMF, a low magnetic field, to a high one, gets involved in time. So the actual shock ramp gets moved upstream of the initial ramp, while the previous one kind of becomes an extended region of high magnetic field, which now corresponds to the magnetosheath. So one can think that there are all those like structures that you see here, which are called slumps, that basically create a reformation cycle when you get a local shock front getting replaced by a new one further upstream, while the old one becomes the magnetosheath. So let's go to the actual result now that I gave you a bit of an overview of the actual theory behind it. So in this example that I will show you, we'll be using the MMS satellite. Usually it is in a tetrahedron format, which corresponds to 4 satellites being very close to each other. However, as a mini campaign, MMS team decided for a few months to put them in this nice direction in the x-axis. So we have MMS 2, 1, 4, and 3 being aligned in GSE coordinates in the x dimension with quite a high spacecraft separation. Of course, high relatively to what MMS usually has, which is far less than the 800 kilometers that you see over here. But okay, let's start to see what the actual spacecraft measure here. So let's start with MMS2. MMS2 in this example is the satellite which is furthest away from the Earth. And I want you to focus between the regions 1 and 3 that I have shown here, just to get a bit of train for the eyes on how we realize that the region between 1 and 3 is actually solar wind measurements. Usually when we observe solar wind and foreshock environments, we expect that kind of correspondence for the bulk data. So we expect a very high Vx component, quite low Vy, Vz, low density, and a low magnetic field. So here you see the dynamic pressure, velocity. Here you see the reduced velocity distribution functions in the x, y, z coordinates, the density, the magnetic field, the ion temperature, and the energy spectrum. So you can see already from the data and also from the very characteristic beam-like distribution that we are in the solar wind environment in this case. Now, if we move to the satellite which is closest to the Earth, which is MMS3, we see a totally different picture. We see actually what we call a magnetosheath region. You can see that we have shocked plasma, or that we have transitioned through the bow shock by the very different properties that we observe. First of all, the most characteristic thing is that we see this kind of thermalized distribution. The energy spectrum now has a much wider spectrum compared to the beam-like distribution of the solar wind. Furthermore, the magnetic field has increased and the density, which shows that there has been some kind of compression to the plasma that has passed through the shock. So basically, those are the two different regions. And the satellites in between see, of course, something in between in the magnetosheath and the solar wind that I show you here. But now we will be focusing on the actual jet observation that is found between the structures 1 and 2 that I show here on the right. So let's see this structure in more detail. Here you see how this actual dynamic pressure enhancement corresponds to the background magnetosheath value and the background solar wind. As you can see, we're talking about a very high dynamic pressure enhancement, far higher than both the background sheath and the solar wind measurements. And as you see here, those are the bulk moments that I also showed you before. And if we zoom now in to the jet observation itself, we will see that we have quite a high velocity for the jets and a very high density correspondence. But this is a very key point that I want to make. Those are the so-called full bulk moments of the flow. But if we look at the middle here, which are the 2D reduced velocity distribution functions, we can see that it is not really one homogeneous plasma population. The actual jets, the actual high dense, high velocity flow that we look is this part of the distribution over here. So this is typically how a jet looks like. It looks like a superposed population on top of a thermalized background in the magnetosheath region. So here is a very tricky point that if we treat the bulk full moments as the characteristic of the jet, we do not see the full physical picture. What we really need to do to understand what is really happening is to get partial moments based on the distribution functions that characterize only the jet flow and not the full plasma that we measure there. And if we do that, what you see is that as expected, we get a slightly less dense plasma, but we get a much higher velocity, reaching 360 kilometers per second, which is pretty much the same as the local solar wind values. So now that I showed you a bit how the actual jet exists and showed you that, okay, we have a clear supermagnetosonic flow residing in the downstream magnetosheath area, we need to understand how this came to be. How do we get solar wind values downstream of the shock? So I will be showing you a sketch that tries to explain the mechanism on how exactly we're able to detect that observation with MMS. So here on the right, we have again the reduced velocity distribution functions for the Vx component. And we start with MMS2, far from the Earth, going to MMS1, MMS4, and MMS3. So you go from furthest to the Earth to closest to the Earth. And here we see a projection on the x-axis and on time for what the satellite measures. So if we look at T1, what we effectively see is that MMS2 sees the very edge of the shock, while MMS1, 4, and 3 sequentially see the magnetosheath region downstream of that shock. So we always need to remember that those satellites are aligned from Sun to the Earth. So what the satellites see at the later time is basically the extent of the structure that the satellite MMS2 sees initially. Now, if we move to a later time 2, we see how the structure that is very visible due to its high dense and high magnetic field moved from being at the edge for spacecraft 2 to be at the edge for spacecraft 4. So now it is a time for spacecraft 4 to observe the very edge of the shock in this example. On the other hand, the other satellites, MMS1 and 2, sees effectively the solar wind, because now the shock front locally, which is a four-shock structure, moved towards the Earth. Now, if we move to time 3, what we actually see is when the time is, when we see the actual jet with MMS3. So MMS3 now sees and measures in the magnetosheath region a high velocity jet. But the question is, why do we still see this jet over here and we do not observe solar wind? And this can be answered by what the previous satellites actually sees a bit like a T4 a few seconds later. So what we see if we focus now on MMS4 is the following picture. First, MMS4 sees the first kind of magnetosheath thermalized plasma. Then it sees a corresponding reflected population and solar wind population that can be seen very nicely in the reduced distribution functions. And then again, it observes thermalized plasma that corresponds to another shock front. So this is pretty important because it says what it effectively means is that we get another shock front in front of the previous one that effectively allows kind of trapping mechanism for the solar wind in between the two structures to continue downstream of the shock. So this kind of creates a reformation cycle, so to say. And if this reformation between 1 and 2 is not extremely clear, I will not go into too much detail, but I want you to see how the reformation between 2 and 3 looks like. So now if someone sees what happened in T1 and what happened in T8, we see an extremely similar situation. Here at T1, MMS2 observed the very edge of the shock, which is pretty much the same thing that happens at T8, again for MMS, for the red satellite, MMS2. Now, because those structures are convected downstream and they move towards the Earth, it is MMS 1, 4, and 3 that basically see the magnetosheath behind those structures. So you can see how MMS2 kind of sees this kind of not fully thermalized plasma. But as you move closest to the Earth, you see how the plasma that corresponds to the downstream part of that object is fully thermalized, compressed, and represents the actual magnetosheath region. And this is where we find the jet. So to give you a summary of what we observed in this work, what we found is that, first of all, and this was kind of expected, the local shock fronts are getting convected downstream. Those are localized structures that are called slums, and they become density enhanced region downstream of the Earth. But what we most importantly observed was that we saw the first in situ observation of jets basically being transferred downstream of the shock due to a reformation cycle of the bow shock of the Earth. So in reality, what happens is that we see those kind of solar wave packets being trapped between solitary magnetic structures, effectively going downstream of the shock due to having, let's say, a shock front appearing upstream of the previous one. So basically, this is quite interesting to see because it's a fundamental process of collisionless shocks when you go to a quasi-parallel shock. And in principle, they should be applicable to any kind of slope transitions that have this kind of configuration. At the moment, we already have started to see a few simulation results that seem to agree with those results. And I have also found 2 more examples with the MMS satellite that kind of show the same signature. However, of course, it's a bit sad, but the MMS satellite usually doesn't have this configuration where everything is nicely aligned in the X direction. So, so far, I've only found 3 cases where we are very close to the bow shock, while at the same time have clear characteristics upstream and downstream of it. Finally, I should mention that we need to understand exactly how the trapping works of this solar wind structure. How likely is that those structures actually survive further downstream, and how prominent this mechanism is compared to the other ones that have been proposed in the past. And in reality, what we should really do is to see whether this mechanism has some kind of prediction regarding the properties that are not similar to the mechanism that I showed initially, like the bow shock ripples or something connected to rotational discontinuities. So that's pretty much my work, and I'm available for any questions that you may have.
Thank you very much, Sava. Very interesting work. The magnetosheath has become a very interesting region. So we already have one question from Tassos Anastasiadis.
Oops, sorry for removing that. Yeah, okay.
Okay, Sava, can you hear me?
Yes, of course.
Okay, so very nice talk, very interesting. It reminded me of work that had been done theoretically by Rob Decker, you know, trying to resolve this problem on the ripples on the bow shock in the beginning of 90s, I think. The question is on how you can be sure that you are tracing the same particle population between, if you put the view graph with the scenario you have between T1 and T8, are you sure that you are tracing the same particle population?
Yes. Okay. So one of the problems, of course, is.
Let me finish the question, and then. Do you have any analysis on the pitch angle distribution of the particles? That's it.
Yes, I haven't done yet the pitch angle analysis, but it is to do it in the future. But I can tell you that one of the main reasons that we believe that this is the case is that what we did was that we cross-correlated the different objects and different structures that we see. And we see that basically all the structures, at least the localized fronts that we measure, for example, the structure 1 and the structure 2, are moving from the sun to the Earth. So they move sequentially from satellite 2 to satellite 3. So we always have this kind of time lag of a couple of seconds that correspond to structures that move with approximately 100 to 150 kilometers per second over the Earth. And while we are not so sure about the exact population that we track, if we look at the reduced distribution functions, for example, as we can see here, we see that the population that corresponds to the jet has very clear properties of a slightly compressed solar wind that has an extremely high Vx component that is very, very similar to the solar wind observations that are close to this so-called Whistler train that is found upstream of the initial shock run. So, of course, yeah, the pitch angle is the next logical step that we should check to see the population around that time.
Okay. Thank you so much. Very nice.
Thanks.